To avoid the memory access penalty for writes, perhaps not to 100%, but to reduce it almost completely, then relaxed memory models should be used. Since supposed to sequential consistency, we don't have to wait for write completion before we can start with the next memory access. Okay, and also there are many optimizations both in hardware and for compiler writers which are permitted with relaxed memory models. Okay, so relaxed memory models, it's not just one memory consistency model, but as we will see, are many, and we will look at some of them. And languages such as C, C++, and Java, they are specified for relaxed memory models. Okay, so in sequential consistency, for a parallel program, it's quite common that threads need to be synchronized. It's very rare that they can be parallelized without any synchronization. And under sequential consistency, we can use plain int variables, and for the synchronization, such as writing to a flag when some data has been modified. And that is not permitted in relaxed memory models because it doesn't work. Instead, system recognized locks must be used. And the reason is that they will perform some additional special instructions that will make sure that the program the thread does not proceed after that point unless data has been synchronized. Okay. So what can be done in a relaxed memory model? First of all, the two constraints, program order and write atomicity, are relaxed, but there are different ways to relax them. What can be done? Here are 6 examples of what we can permit to be reordered. So say we have 2 operations from one thread, A and B. And when we say that we relax them, we mean that A is supposed to be executed before B, but with relaxing them, we permit B to be executed before A. Okay, so we can relax write and read program order, and write and write, and read and write, and read and read, and read another CPU's write before it was completed, and read your own before it was completed. And the different relaxed memory models, they will permit different subset of this. So there are some assumptions for this to work. Firstly, all writes will eventually be visible to all CPUs. That means the cache queries protocol, and the cache and the memory, they just don't stop, but they continue working and send messages, etc. So eventually things will propagate to where they should be in the machine. Okay, and also that writes to a certain cache block, they are serialized by the memory, just as in sequential consistency. So it would be extremely complex and completely nonsense to let different CPUs write to the same variable at the same time and update the memory. Instead, it is they update this memory block in a sequence. Okay, but they don't have to wait. They can continue with the next instruction anyway. And also that the uniprocessor data and control dependencies are enforced. What does that mean? Well, it is what we expect from a computer, namely that, well, first, data dependencies. It means that if we write to a variable x and then read, we should get the latest write that we did. Okay, and control dependencies means that if we evaluate an expression, then we should not, I mean, in an if, for instance, we don't execute the then statement regardless of the condition was true or not. I mean, this is so obvious. So it is, I mean, that's needed to make any computer work, but it still has to be an assumption for relaxed memory models to work. Okay, so what will happen if we relax the write to read program order constraint? And first of all, this means that we assume different addresses. Otherwise, it would be obviously wrong program. I mean, if we would skip, if we first write x and then read x, the read should clearly use the new value. Otherwise, it will be completely wrong. But if we may execute the read before the preceding write, then Decker's algorithm fails, as we saw with read bypass. So if we would do this read before that write, both can enter the critical section. Okay, so let's look at some relaxed memory models which permit reordering a write and a read pair. Processor consistency from University of Wisconsin by James Goodman, and weak ordering and release consistency, and some from IBM and from Sun, now called Oracle, and Intel. Okay, let's go on to others. Write to write program order. What that means is that these two writes can be reordered. That can be quite disastrous if we don't expect that to happen. Okay, so models which permit this reordering, now it's fewer. Weak ordering and release consistency and IBM power. Partial store ordering and relaxed memory order. The total store ordering, this one, clearly does not allow it, since, I mean, that's the point of the total store ordering, to not reorder them. And what we can see here is that Intel does not allow this, which means if we have written a program for Intel, it might work on Intel, but not on more sophisticated relaxed memory model, such as used in Java or C or C++. Okay, so if we only require the uniprocessor data and control dependencies, and it can change the order of any memory access, then we have this remaining. And I should say also that ARM is similar to Power. And what they do is to permit extensive hardware and compiler optimizations. Okay, so now we come to an obvious question. How come we can write any working parallel program if all the memory accesses can be reordered?